Let's now consider a brief summary of dynamic programming as a way of calculating value of a state. First thing to notice is dynamic programming is something which uses what's called a full backup, right? And a full backup basically means if we look at where we start in state space, what a full backup means is it considers all the actions we take from that state. So if in this particular example we're just showing 2, and then from all of from the state we started and given all the actions we take, it all then considers all the possible states we can actually end up in. And it's looking at all the actions and all the future states S prime that can arise from a given state. So that's why it's full backup. It's using all the possibilities from that state in one step from where we started. DP is very useful then for things like iterating the policy in order to actually improve what we can do to get the most gain from a given state by taking the right action or the best action. It's also very good for working out what the overall value of a state is as well, from basically by just calculating many times and iteratively updating what the value is. Like I said, it's full backup, which means it considers every successor state from a given state and every action from that state. And to do so, it needs knowledge of the Markov decision process. It needs to know the transition function and the reward function in order to be able to take to adopt this approach. So it takes an action in order to find out where we're going to hopefully end up using then what is then the stochastic state transition probability, which leads to looking into how do we get into one of many future states from that point. It can be effective for medium to small size problems. If the state space becomes big, it's not computationally practical to actually use this approach anymore. It suffers from what Bellman described as the curse of dimensionality. And the curse of dimensionality really relates to the fact that if we've got a large number of dimensions to a problem, then we start having real problems. And they really are gigantic problems. It's not that it's just inconvenient or take a long time. It becomes absolutely impossible to calculate these things. There's more possibilities than atoms in the universe kind of thing. Right? So it's really a serious issue at a fundamental level. And so there are other approaches that can actually deal with estimating value and doing reinforcement learning that don't need all the parameters, all the model we have in a Markov decision process. So if it's model based, then we do have these things. We do have the transition function, and we can evaluate this Markov decision process. That's what DP does. But it does need this model of everything and the model of environment. But we can also have approaches which are what's called model-free approaches that don't actually have all of the information about the Markov decision process, and they can approximate value function just by trying things out from experience. They don't need to model this transition function. And one such method is Monte-Carlo. So probably the name Monte Carlo would immediately conjure up ideas of going to the casino in Monte Carlo, suggesting that things are a bit random and there's a chance of getting something, and hopefully in this case, well, the Monte Carlo, hopefully you'd like to win a lot of money. But that's really the way these things work. They're sort of sampling methods, stochastic methods to actually find solutions to problems. So like we said, DP needs this probability model. It needs this model of the state transition probability. What's the future state S prime given the current state and the current action we take? But we don't need that with model-free methods. That's the nice thing about it. So in these methods, such as Monte Carlo, we can estimate value of a policy, right, just by trying things out and seeing how we get on, right? So we don't need to have this prior model. We can actually run it in a simulated or a real environment and actually estimate what the value of things are just by experience. So the way we do this is we try things out. If you're in a maze, for example, you'd be in a state and you just try to get to the goal, right? And hopefully you can finally get to the goal. So every time you get to the goal, by wandering around through some pseudo-random path, you end up to the goal. when you get to the goal, that counts as an episode. So you started and you finished, so that's an episode. And you can do that many, many times. And when you start from a given state, you just carry on until you get to the end, but then you can say what the value of the starting point was, because you can add up all the bits all the way along the way, getting punished by every time you make a movement, by getting a reward when you get to the goal. And if you run this multiple times, you can average the final value that you've got from a starting position in order to get the average or the expected value from that particular starting position or state. An example would be, let's say in one episode you start with state 1 and you go to state 2, you go to state 3, you go to state 4, you go to state 5, then you get your reward and it's terminated because the episode's come to an end. You got to the goal. You can then say, well, I got certain value from this. I might have had a cost of moving from 1 to 2, 2 to 3, 3 to 4, 4 to 5, but then I got a nice big reward at the end. So you can then say, yes, I can already say what kind of value I have in state 1, for example. But it could be that then you do another run, another episode, you go from 1 to 2, 2 to 3, then you go from 3 to 2, then you go 2 to 3, then you go 3 to 2 again, and then you finally go straight and straight and straight. In this case, you'd have lost a bit maybe going round this loop a couple of times, so the overall value from that particular episode would be less. But what you do is you run it loads and loads of times, and you calculate the average over lots and lots of episodes in order to get an idea of what kind of value you've got from a starting state. And these are generally, Monte Carlo methods are generally applied to episodic tasks. That's, in mazes, for example, that's how we're going to look at them, which do terminate, right? And if they do terminate, then we don't necessarily need a discount factor. So what we see with Monte Carlo, it's a very noisy process because you're running it all over the place. So it's got what we call high variance because it means that we've got to do lots and lots and lots and lots of episodes in order to get a good estimate. But it's not biased in any way. That's the good thing about it. And it is shown to be have good convergence properties. So if you run it many times, it will finally converge to what we think is the real value of this actual state. And it's really robust in terms of what the initial values were in the estimate. So it's not sensitive to that initial values, and it's pretty easy to understand. You just, like I said, you just start somewhere. It could be starting 2, going 3, 4, 5, and then you look at what the value is by the time you get to the end, and you can say, well, that was my first estimate for this episode. Easy to understand. So what we want to do then is actually say, right, the value of a state is going to be the expected value of the gain from that state. So given I'm in a certain state and I'll end up getting to the goal, I know on a particular run through the maze, a particular episode, what value I got from that. And all we have to do is calculate on average what do we get from doing that when we do it multiple times, and that's then the expectation of what we get from that particular state. Now, if we want to do that for a system that never actually sometimes finds the goal, then we definitely need to discount the reward that we get. Otherwise, this thing runs forever, right? And it'll not necessarily converge. In which case, we'd use the discounted reward. We have this way of saying that every step that we take from where we are is less and less and less important, and we can do that with this gamma value, which is between 0 and 1, which then basically starts off being reduced by increasing the power that we multiply the future value with. Again, we can then substitute this discounted reward into our expectation function. But, if we're using episodic tasks, we don't necessarily need to have anything other than gamma equals 1, because it's going to terminate anyway, so we will get a finite value back. There's two ways of actually doing this Monte Carlo as well. We can either say we're going to start in a particular state and then see what value we get when we get to the end, and that's it. Or we can actually say we're in a particular state, and every time we come back to that state, we can also say that's another starting point, if you like. So the first visit Monte Carlo is where we start off in a particular state, and then all we do is just look at what happens when we get to the end, and then we associate that with the value of starting in that particular state. That's first visit Monte Carlo, because that's the first time we were in a state. With every visit, every time we go back to the state, we can say, well, that's the start of another kind of path that we can do. So we could actually use all of those paths as well and use that as part of the update. So we do multiple updates from a single episode because it hit the state several times as well. So we're just going to think about first visit here, right? So we know that effectively to calculate this, then we need to know the gain from a particular state and calculate the expected value. And to do so, we need to look at the gain we get over multiple episodes, trying it loads of times in order to get the average value. So what we're going to do, if we have this first state approach, we start off in a state, and over different episodes, we just count the number of times we'd actually started in that state. So we're just incrementing the visit counter. And then we just, across the different episodes, having started in that state, we add up the total gain that we got across the episodes. And then in order to calculate the value of the state that we started in, we just say it's just the summed value of the total gain that we got across all the episodes divided by the number of times we started from that particular position. And of course, as the number of episodes goes to infinity, then the value estimate that we get should be a good representation of the value of that state under the policy which we're actually evaluating. Right. So this is using then, if we do that then for this other condition where we're using every time visit, that's slightly different. All we do then is every time we hit that state, we say we've been in it. So we could count in an episode could actually result in several counts for being in a state, and the total gain that we get from that state obviously then will add up from each time we were, from every time we started from that place. So you end up with, if you like, you could have several updates for the number of times you're in that state and several updates for the gain you get from going through a particular state. But apart from that, it's quite similar. We're just, like I said, I'd consider just first of all starting with first visit. And we know incremental means are also possible to calculate. We did discuss that. Rather than just saying that we've got all our episodes, we know all the actual starting positions, we've counted them up, how many times we started there, and we sum up all the values, and then we say we're going to add up all the values and we're going to divide by the total number we've got. Then that's one approach of doing it. But we can also use our incremental formula. So we could say, rather than calculating the mean by taking all the values, adding them up and dividing by the total number, we can also, if we remember, we can also split up such that we've got the mean up to n-1 steps, and then we can just add on the mean from the latest episode that we do quite easily. We don't have to do the whole calculation again if we don't want to. We can do this online update like we did before. So rather than just making sure that we've got all the values of the gains and then divide by the total number of things we did, we could take all the last values of the gains and then do another episode and update what we have for the value. So just like we do with calculating the mean, we use the mean for the n-1 values, and then we add on a scaled version of the new value, take away the old value, and to do it in an incremental way. And we use that with Monte Carlo, and we'll use it with temporal difference as well a bit later on, because it basically just means every time you do something you end up updating rather than calculating all the raw data and then calculating the total number of times and dividing them. So Monte Carlo by incrementing is calculated then by incrementing, as we know, the number of times we visit a state. We can calculate the incremental mean then of the value by updating the value that we've got now with the last value we had, and then just scaling the new by 1 over the number of states we had, scaling the additional gain that we get, take away the value we had before, and running it in an incremental value, right? In an incremental way. And we see that this formula then is just the update rule again that we've seen in lots of cases. The updated value is the previous value plus some learning rate, take away what we've got now coming in for the new value estimate, take away the previous values, right? And this again is just incrementally calculates the mean, and the alpha is just letting us slowly forget the past as well, right? So the important thing about Monte Carlo is it's not a full width method, but it's a full depth method. What we do in Monte Carlo, this is looking at the backup diagram here, is we start in a state, then we take an action, and then we go to another state, and then we take another action, and then we take get to another state, and then we take an action, and we finally end up in a terminal position because it's going to terminate at the goal. So we've got really just a path all the way through some kind of state space. Here's just the steps that on this sort of y-axis is the steps. Start off here, take an action, end up in another state, take an action, end up in another state, take an action, and finally end up at the terminal state. So what we see is a single path all the way through the system. We're not now exploring after the state here, the starting state, all the actions. We've taken one action, and we're taking no notice of anything else we could have done. We're just looking at what we actually did. And again, when we take the action, we end up with a particular state. We don't consider the rest of the states that could have happened. We are only in that state. So what we see is it's a very deep backup. It goes all the way through, all the way to the goal, but it's got a single width all the way down. So it's actually something which is very deep because it goes all the way to the end. So it's not doing just an update on the basis of the current state, current action, and the next states. It's doing a backup now in terms of going all the way to the goal, but it's only considering this single path, right? So it starts in some states. So it's a complete trajectory all the way to the termination, but it's not broad. It's a very narrow update. Okay. So policy evaluation, that's basically just to work out the value. So given the value, then given the particular policy, we can compute the state value. We're only going to consider a first visit here. This is just basically the Sutton and Bartow pseudocode for doing this first visit estimation of state value. Initially, what you do then, well, obviously you've got to have a policy, right? You've got your policy that you want to evaluate. That's what it's doing. It could be random, but it could be something, that's maybe biased into giving you good values and good results. First thing we do then is initialize our values. You could always set them all to 0. We're gonna make lists of going through. Then what we've got is a loop which does, for each episode that we actually run, we're going to run, we generate an episode. So in other words, we start off in a state and we end up taking an action, going to another state, taking an action, going to another state, taking an action, going to another state, all the way through until we get to the goal. And we record all of those things that we're doing. And we look at the goal state value and stuff, and we're looking at the state sequence, the action we took, and the reward on each step. Then what we do is we're going to then process each episode, right, through each step of each episode, and we're going to calculate the overall gain that we get. The way it's been written here, it's actually you're doing it in a discounted way. But if we didn't discount, we're just summing up all the rewards all the way along, basically. And then all we have to do is, after we've finished that, we just have to calculate the average total reward across all of the actual episodes we did. And that's the way it works.